All right, so I wanted to just talk through this Q1 from section 3.5 since I chose to make this really hard. I wrote a bad one and then I fixed it and the fix was bad. And then I made a question now that I really like but is maybe a little bit more involved than I thought. That being said, this does look a lot like a question that I'm planning on asking on our test at the end of next week, so I figured I should just explain this completely, how I think about this one here, so that you can do something similar to this. Finally, I'd like to say before I start here, section 3.7 is going to make this only about half the amount of work that this is right here, and it's going to allow us to draw a really nice picture to answer this a little bit more simply. But I think that since this is all just a bunch of quadratic math, we can definitely handle this without having gotten to section 3.7. So let's go ahead and talk through this. In this question here, we're given this A matrix here with the entries of B, 3, A, and 2. And we want to talk about classifications of this matrix based on its eigenvalues. So I'm going to go ahead and compute the eigenvalues, and that's what you can see happening here on the left-hand side of this page. I set up my B minus A and my 2 minus lambda. As is typical for me, I am always going to factor out a negative from each of those expressions. I want to look at this as like a quadratic in lambda, so I like to have lambdas be my first term and my positive term in each factor there. So again, I factored a negative out of each of these two terms, which is canceled away, allowing me to write these two sort of backwards right there. Minus 3a. When we expand these, we're going to get negative 2 copies of lambda as well as negative b copies of lambda. So we see the negative 2 minus b copies of lambda. And for our constant coefficient on the end, we get negative 2 times negative b for positive 2. Minus 3 is going to be equal to 0, setting our determinant equal to 0 there. We can then go to the quadratic formula now. We have something quadratic in lambda that is equal to 0, so I write this in the quadratic formula. Notice again, I'm going to do some negative factoring here. Negative 2 minus b, when we apply a negative to that as our b term here in the quadratic formula, they both become positive. Also over here, when we have a negative term that is being squared, that's the same as a positive term being squared. So in a sense, I already squared away the negative for the negative 2 minus b to make it b plus 2. Then we have our minus 4ac term, minus 4 times a is 1. Our constant term on the end, our c, is 2b minus 3a, and we're all divided by 2. Just to do a little bit of simplifying here, I expand b plus 2 squared as b squared plus 4b plus 4. And I'm going to distribute the negative 4. Negative 4 times 2b is negative 8b. Negative 4 times negative 3a is positive 12a, all divided by 2. And we do one last little simplifying step here. Positive 4b minus 8b gives me negative 4b underneath the square root. So it looks like this is the cleanest I can write my expression for lambda here. And if I were to know values for a and b, I could easily plug them in and find them. But we're going to go the other direction with this. Instead, we're going to say, rather than being given A and B, I'm going to say I have a desired classification for this system, and I want to know what A and B will fit that. So suppose that my desired classification for the system was that we are a degenerate sink. I want to know what values of A and B are going to make this happen. So if we're a degenerate sink, then that means to me we're going to have repeated eigenvalues. If we have repeated eigenvalues, that always happens when our discriminant term with the quadratic formula is equal to 0. Further, since that's just the degenerate part, the sink part then is also going to tell me that whatever I get when my discriminant goes to 0, I'd better have negative lambdas, not positive lambdas, because I want to experience sinking. So notice when we look back at our old lambda statement over here, I'm looking for the discriminant to go to 0 so that I get repeated eigenvalues. So that should leave my lambda term just as b plus 2 over 2. So I've got that right here. Lambda will be b plus 2 over 2 because the discriminant will be 0, and I need to make sure that that term is negative so that we're not just degenerate, but that we are a degenerate sink. So I'm going to go ahead and set my discriminant equal to 0 right here. Since this is another quadratic in b that is equal to 0, I can again use the quadratic formula, but notice this is doing something different. This isn't lambda anymore. This is determining what values of b are going to satisfy our discriminant being equal to 0. So in this case here, I'm going to get my negative 4 term squared is 16 minus 4 times a times c. That's going to give me negative 4 times 4 plus 12a divided by 2, underneath the square root divided by 2. So here, what we're going to see under the square root is we get a 16 minus 16, and then the negative 4 distributes to the positive 12a to give us a negative 48a that's going to remain underneath the square root. So it's a little fuzzy right there, but there's our negative 48a underneath the square root. I'm going to do some simplifying. 48 is 16 times 3. Square root of 16 is 4. So I'm going to rewrite this guy. So 4 divided by 2 gave me 2. I had a 4 that popped out here as well. 4 divided by 2 gave me 2. plus or minus in between, what remained underneath the square root was our negative 3a right there. So that's going to be b. But I don't just need to find the relationship between b and a. So this tells me the relationship between b and a for us to be degenerate. But what I want to do is verify that we're going to be a sinc. I know that my lambdas are going to take on the structure of b plus 2 over 2. So I want to ask myself, are both of these b values going to result in us having a sinc? And what I can see is, if we choose the positive number right here, 2 plus 2 times a positive number, that's all positive stuff. Positive plus positive divided by positive, that's going to be positive, and I want to be less than 0. So since I want to be less than 0, I'm going to only take a look at the negative part of my b value right here. So 2 minus 2 times negative, the square root of negative 3a plus 2. And I just want to verify this is going to be less than 0 right here. For what values of a are we less than 0? So just doing a little bit of solving here. Multiply the 2 away, add our square root term to the other side over here, square both sides, and divide by negative 3, being sure to flip my inequality when I do that. And here I'm finding that a needs to be less than negative 4/3. As well as having this relationship between b and a. So this relationship between b and a guarantees that we're a sinc. This interval of I said that backwards. This relationship between b and a guarantees that we are a degenerate sinc or source. To guarantee that it's going to be a sinc, we need to make sure that our a value is less than negative 4/3. Okay, so that's getting us our degenerate sinc. Now I'm saying to you, I'm giving you a little bit more of a specific example here and talking to you about sinc versus source here. So if I tell you that a is going to be negative 4, then my question to you is, what b values are going to give us a degenerate sinc or a source? So I know that my relationship between degenerate sinc and source is going to have to be that b is going to be 2 plus or minus 2 square root of negative 3a. And I know what my a value is. So I'm just going to plug in a equals negative 4 into each of these two possible solutions, right, or into this solution right here with the plus or minus. And then I'm going to consider the positive route, and I'm going to consider the negative route. If I consider the positive route here, I can see that with my lambda being b plus 2 over 2, I am going to get positive lambdas. So if a is negative 4, I should be getting a degenerate source. And alternatively, if b is going to be 2 minus 4 root 3, I can see that that's going to give me 4 root 3 is bigger than 4. So 4 minus 4 root 3 is negative, less than 0. So in that case, we should be getting a degenerate sinc right there. Okay, finally on to the last part here. Different lighting on this page right here. I don't know why. If b is equal to, so now we're walking away from the degenerate thing, by the way. So notice all this degenerate computation that we're doing is all based on this discriminant term being equal to 0. I'm now no longer interested in necessarily seeing a degenerate sinc or source. Now I'm just saying I just want a straight up source for this. So what that means to me is I am interested in having both of my lambda values be greater than 0. And so the piece of information I've been given is that b will be 0 in our equation here. So I'm going to apply b equals 0 to what we had previously found to be our general eigenvalue equation here. And I get this much simpler statement right here. And again, what I am interested in finding here is under what circumstances are we going to have both of our lambda values be positive and real. That will give me a source. So if we're going to get positive for our two eigenvalues here, what's really going to have to happen is we need to make sure that when we do 2 minus this number, we can't subtract off a number bigger than 2 here, or else that guy's going to end up being negative in the numerator. I want to have 2 plus some number and 2 minus that same number both be positive. So it needs to be that the square root term is smaller than 2, so that when I subtract it from 2, I still get positives. So I'm going to set the square root of 4 plus 12a to be less than 2. Square both sides, subtract 4, and we really just see that a needs to be less than 0. And notice if we just plug in a equals 0 right here, we're right at our fringe case. If a equals 0, we get 2 plus or minus 2, which gives us 0 and 4. That's almost positive. That's 0 positive. Anything where a is less than 0, we will fall into the positive category. But as our last thing to state here, notice that making a less than 0 doesn't guarantee that we are just a sinc. Look back at our original lambda equation right here. If I plug in a is like negative a billion, then it's certainly the case that we're going to be getting a negative underneath the square root. That would be a spiral, maybe, source, and I just want a straight up source. So I also want to make sure that my discriminant term here is positive. My 4 plus 2a needs to be, 4 plus 12a needs to be positive to make sure that we are not a spiral, that we're just doing a real valued source. If that's the case, then we're going to find that a needs to be bigger than negative 1/3. And so we can conclude by saying if b is going to be equal to 0, then the only little interval of a values that's going to give just a plain old source is the open interval from negative 1/3 up to 0 right there. We found that a needed to be less than 0, and then it needed to be bigger than negative 1/3. You can just see I just typoed right here with my brackets. Those should be parentheses right there. So again, maybe a little bit of a hairy problem, but this is really just a whole bunch of quadratic formula analysis here. Again, I am going to ask you a question pretty close to similar to this. I'm planning on just making some matrix that looks a lot like this A matrix with some unknown coefficients in it and asking you questions like this. What's the relationship between A and B if we're going to have this type of classification, stuff like that. But again, section 3.7 is going to do basically exclusively the job of helping us to classify easier, and it's going to give us a visual to where we can help picture what kind of answers that we're getting here rather than just trusting only our algebraic parts here. So if you have any other questions about this, certainly feel free to ask.